So we are talking about population growth. Yes, because we talked about what ecology was on the last day that we were here, Tuesday. Y'all described populations with your hybrid assignment from yesterday, and today we are talking about population growth. How we measure it, why we care about it, and the different types of population growth that exist in different populations. Beautiful. All right. So there are a couple things that determine population growth. So factors that affect population growth. We're going to write population out a lot. So I'm going to start abbreviating it to POP. You can write out all of population if you want. You can abbreviate it if you want. Do not care. They're your notes, as long as you know what's going on. The first one we're going to talk about is births and deaths. Naturally, our population is going to be affected in size by the rate at which things are born and the rate at which things die. So, birth rate is also known as natality. Death rate is mortality. So, if the birth rate is higher than the death rate, our population will increase. If the birth rate is lower than the death rate, population will decrease. Essentially, if more people are being born than people are dying, then our population is going to rise in numbers. And if people are dying faster than they're being born, population will drop. That's a D. That's also D. The other factor that affects population growth is immigration and emigration. So immigration are individuals moving in. Emigration are individuals moving out. Think M moving in. Think E for exit. So the rate at which individuals move into a population and the rate that individuals move out of a population contribute to growth, i.e., if our birth rates and death rates are stable, like the same amount are being born as die, then our population stays the same. If more people or more individuals are moving in than are moving out, population will grow. But if more people are leaving than are coming in, population will shrink. Yes. We also have something called migration. If you see the word migration is in here, essentially that is the seasonal movement of individuals in and out of an area. In the summer, our population of Canadian geese is much higher than our population of Canadian geese in the winter. So populations can shuffle and fluctuate over the course of a year just based on the seasons. When we talk about birth rates and death rates, so if we kind of go back up and connect this a little bit, we have to talk about something called survivorship curves. Essentially, individuals of different ages have different probabilities of dying, and that can be modeled with a survivorship curve. So, survivorship curve models the likelihood of death with age. Oh, sorry, because individuals at different ages have different probabilities of dying. There are 3 types of survivorship curves. 3 typical models for the rate at which organisms die based on their age. So, extend this. So, type 1, type 2, and type 3. When we talk about curves, we are talking about graphs. So, actually, we'll do it in blue because these are all going to be the same. So, on the y-axis, we have the number of survivors. And on the x-axis, we have age going this way. Now, here's a question. Can I Oh. Okay. Oh my goodness. I'm a technological giant. This makes me so happy. All right. So we've got our 3 types of survivorship curves. The first one, our type 1 survivorship curve, is like humans. We have a type 1 survivorship curve, meaning that mortality, so death rate, increases with age. Death rate increases with age. So it looks kind of like that. That's type 1. So when you're young, you have a there's a lot of young people, a lot of young survivors. As you get older, your likelihood of dying increases, which means we have less old people than we have young people. That's typically how it goes anyway. Type 2 survivorship curves are like birds. A lot of birds have type 2 survivorship curves, meaning the death rate is equal at all ages. You have the same likelihood to die as a chick as you do as an old bird. So death rate equal at all ages. So it's just a straight line down. Same rate of death, which means that as organisms get older, there's less and less of them, but that pace is the same. Meaning between this point and this point, the same number of people died. So we'll say there's 10 birds there, 10 birds there, 10 birds there. Does that make sense? Whereas with our humans, we'll say we lost 1 here, we lost 3 here, we lost 10 here, we lost 30 here. If that makes sense. Okay. Type 3 survivorship curves have a higher rate of death at a young age. High death rate at a young age. This is usually in organisms that have a lot of babies. Like toads. Toads. Meaning one mama toad could have like thousands of eggs, right? But of those thousands of eggs, only a couple of them mature to be like actual frogs. So it looks kind of like that. Meaning a bunch of them die at a really, really young age, and only a few of them live into old age. So, any questions about survivorship curves? No. All right. So, another factor that affects population growth is age structure. So, age structure is determined by the relative number of individual within a certain age group. There's a way that people diagram these that I'm going to show you really quickly. You will likely see these again, but I just want to show you while I'm talking about it. So this is an age structure diagram, or 3 different age structure diagrams. The blue is ages, you can't really see it, but like 1 to 14. This is like 20s and 30s. This is like 60s and above. So like there are this many 0 to 16-year-olds, this many like 18 to 30-year-olds, and this many certain old people. So, oh no. This is important because more young people in a population means that populations are going to increase. More old people population will decrease, and if they're even, our population is going to stabilize. Which makes sense when you think about it, because if there are like 70 people like our age, but like only 20, 30 people who are like 60s, 70s, we, our like age group is the group that will eventually maybe go on to reproduce, but our old people can't anymore. So with more of the population having the potential to reproduce means we are more likely to get more babies. But if we've got like 70 old people and only 20 young people, those 20 young people aren't going to be able to make enough kids to like grow the population, because those 70 old people are going to die faster than they can reproduce. So this population, if this were to like move up, essentially would just go outward like this, right? Because they would have more babies and they would have more babies until it got really big. This one's about stable, but if it were like this, then these guys would all die off and this would eventually funnel out. That makes sense? Okay. That is age structure. Talked about immigration and emigration already. Now we are going to do a little bit of math. That's not what I wanted. Math. So we are going to calculate population growth. Calculating population growth. So your growth rate equals the individuals added minus the individuals that leave. Makes sense, right? So our individuals added is our birth rate, so how many are being born, plus the immigration rate. So our two sources of getting organisms or getting individuals are being born and moving in. So our individuals added equals birth rate minus, or birth rate plus immigration rate. Our individuals subtracted equals our death rate plus our emigration rate. This will give us our net change in size. So overall, how many are going to, how fast is our population growing? Net change in size. And is usually reported as change per 1,000 individuals. Change per 1,000 individuals. So if overall total we are gaining 7 people a year after we get through our birth rate and death rate and all that calculations, if we are overall gaining 7 people a year, our growth rate would be 7 over 1,000. So we're going to do an example. So if we have a population, our birth rate is 18 per 1,000. So for every 1,000, let's say we'll use birds. For every 1,000 birds, we're getting 18 babies. Out of every 1,000 birds, we're getting 10 deaths. That's our death rate. Our immigration rate, we are getting 5. So 5 birds immigrate out of every 1,000. And our immigration rate is 7. And out of every 1,000 individuals, 10 of them are dying, 5 of them are coming in, and 7 of them are leaving. So remember, we've got our formula, which is birth rate plus immigration rate minus death rate plus immigration rate. It would be 18 plus 5 minus 10 plus 7. $23 minus 17 equals 6 per 1,000. So for every 1,000 individuals, on average, we are gaining 6. Doesn't matter where from. Our growth rate is 6 out of 1,000. Six divided by 1,000 is 0.006. We're going to make that a percentage, so multiply that by 100%, and you get 0.6%. That's our growth rate. Are you following in general? I know you weren't expecting math today. So now we've got types of population growth. Yes, types of population growth. Where we're headed next. There are two types of population growth. Two types: exponential and logistic. So our exponential growth is where our population grows at a fixed percentage each year. So it'd be like our 6% growth rate, right? Our 0.6% growth rate. If that was the same every year, if nothing changed and it was always that 0.6%, always that 0.6%, and it never, ever stopped, we would have exponential growth. So population grows at a fixed rate each year. Now, this doesn't happen a lot. Usually when it does, it is when a population is really small and conditions are ideal. It can't grow forever, essentially. Something's going to stop it. We're going to talk about what's going to stop it. Exponential growth, this is our chart, and this is time, and this is our population. Whoop. Go straight up, eventually. Much more common, we will get logistic growth. In a logistic growth, the population is restrained by limiting factors. Population is restrained by limiting factors. A limiting factor, that's a buzzword. I would highlight that one. Underline it, put a star by it. It'll pop up a lot. Limiting factors are characteristics of environments that limit growth. Characteristics of environments that limit growth. So if we've got a farm and we've got enough space for 60 cows, it's a lot of space, but we can only feed 40 of them, the rest are going to die. So our food would be our limiting factor, because our food is determining how many cows we can keep. Limiting factors determine carrying capacity. Carrying capacity is also another one of those buzzwords. It's the maximum number of individuals a community or an environment can support. The maximum number of individuals an environment can support. So we've got our chart again with our time and our number of individuals. Our logistic growth is going to look a lot like exponential at first. We're going to have a period of exponential growth in the beginning until eventually it reaches carrying capacity and it levels off. This right here is our carrying capacity. So it's going to grow and grow and grow and grow and grow until can't grow no more. Don't have the resources. So if you're looking for a definition, logistic growth describes how populations initially experience exponential growth but are eventually slowed and stopped by limiting factors. But are eventually slowed or stopped by limiting factors. See, yeah. Look back up at our graph. We've got our period of exponential growth. So our growth rate is fixed, meaning we're just going to keep increasing and keep increasing and keep increasing until eventually our growth is slowed and stopped by our limiting factors. Tragically, in nature, it's not quite that simple. These are excellent models to show us a general idea of what goes on. But in reality, stuff's a little wonky. So, in nature, populations can fluctuate or cycle through carrying capacity. Near carrying capacity. So if this is our logistic growth curve. A lot of the times, I clicked it. If this was a real population, it can fluctuate. So it'll go up, 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 and it'll just kind of flirt with that line, going up and down and up and down. Or it can cycle, where it'll go up, reach carrying capacity, come back down, go up, and cycle like that. They can also rise and crash. meaning they can exponential growth, exponential growth, exponential growth, boom. Exponential growth, exponential growth, exponential growth, boom. And again, it's not quite cycling because cycling recovers a lot quicker, and a lot of the times the descent is less rapid. So it would be like going up, slowly coming back down, as opposed to our going up and boom. Another little caveat is that carrying capacity isn't always the same. Carrying capacity changes. So there might be some years where we experience droughts. Those droughts would lead to less food, which would lower carrying capacity. Or let's say a disease wipes out a bunch of the wolf population. Well, now those wolves aren't around to eat the rabbits, so the rabbit carrying capacity just shot up. One more thing. We got time. I believe in you. We're going to talk about types of limiting factors and biotic potential. Types of limiting factors and biotic potential. There are two types of limiting factors. The first is density dependent. The other one is density independent. My little button went away. Can I get this page longer? Nope. All right. So we're stuck in this little bitty thing. So density dependent factors depend on density. Density dependent factors depend on density. That's like competition or disease. If there's a lot of a population, there's a bunch of organisms packed together, a disease is more likely to transmit through there and it'll take a bunch out. So the bigger the population, the more likely it will have an effect. Competition's the same way. The more organisms that live in an area, the more likely they will have to compete for resources. Density independent factors are not affected by density. And that'll be like our natural disasters. It doesn't matter how many there are. Forest fire's going to wipe out all of them no matter what, you know? I got to go up and erase a little bit for biotic potential. You guys have this? Biotic potential is the maximum ability to produce offspring. Biotic potential is the maximum ability to produce offspring. Things like how many babies at once? Or how many times can a an organism have babies? And how long does gestation last? So organisms like those toads that we talked about have a lot of babies all at once. They can have babies a lot of different times in their lifetime. And their gestation, or how long it takes for those babies to grow enough to be organisms, is relatively short. Or yes. People, for example, have a lower biotic potential because there's usually only one, maybe two, occasionally three babies at once. If we're excluding the 19 kids and counting John and Kate plus 8 people, excluding them, they're outliers. How many times you can be anywhere from 1 to 6 before it starts really taking a toll on somebody's body. And our gestational period is 9 months. Elephants usually only have one baby. And usually only once, maybe twice in their lifetimes. And gestation is really long. Let's look it up. How long is elephant gestation? "22 months. That's almost 2 years to grow a baby elephant. So elephants have even lower biotic potential than humans do, who have even lower biotic potential than frogs or fish do. I just dropped my mouse underneath my desk. All right, so